Right, you've got about 6 more seconds of that, so enjoy it. Soak it in. And
build the bridge.
There we go.
Cry a river. Crossover.
Step 1, curl up into a ball. Step 2, don't cry. Step 3, don't stop crying. You know this one? Right. Continue. Latent heat is next. Can you write that down? Latent heat. I actually think this is your physics, right?
Yeah.
This one, are you going to stay there for the rest of the lesson?
Where is Faisal?
It's only like 15 minutes. Yeah.
No, still have math.
Oh, we still have more.
We're here till 5, bros. Yeah, I know that feel.
Can we end earlier today?
Did we pretend I'm not here?
Yes, let's all do that. You know what's better than pretending you're not here?
Yeah.
Actually not being here. Faisal, are you ready to continue or have you passed out?
I don't know.
Well, I'll continue, but you can take your minute, okay? So latent heat. This is the class I wanted to be filmed. What's happening right now? I want this to be in the YouTube video. Right.
New studying methods.
Advanced studying methods. Okay. Consider a block of ice which is slowly being heated. That is, a fixed amount of heat is being pumped in per time. For example, 4,200 joules of heat is given to a block of ice per second. Okay. That is 4.2 kilowatt kettle or something is heating up the ice. So, the temperature of the ice will increase, right? If you put more heat energy into it, what will happen? The temperature will increase. And let's look at the graph of temperature against energy. So we get this graph. Now, what's interesting here is as you put in more energy, the temperature increases. That's not interesting, but the interesting part is here, you put in more energy, but you get no change in temperature. And then it continues. And then here, you put in lots of energy, nothing's happening to the temperature, and then it increases. Smooth.
I'm back.
Okay, so you all probably know this from high school, but what's happening here? Why is the temperature not changing? Yeah, because the energy is being used to change it from a solid to a liquid, and here from a liquid to a gas. So this energy, what?
This is a different coffee. You don't drink this every day.
No, it's my lip balm you're smelling. This is a delicious mixture of coffee, milk and lip balm. Tasty.
Did you call him Mr. Lover?
No.
Did you repeat that part again?
Yeah. No, do not call me Mr. Lover or Mr. Bombastic or anything like that. What's happening here is, as you're putting energy in, the temperature increases. That's not a surprise. But at this point, more energy does not equal more temperature. The temperature is staying at 0, and then it continues. So what's happening is the energy is being used to change it from a solid to a liquid. In other words, it's melting. And this requires energy.
And that's why the temperature does not change.
Yeah, because the energy is like it's being diverted from changing the temperature into changing the state.
I need that for my chemistry lab.
Good. That's what we're doing today. Guys, can I continue? Okay. So this gives us the concept of what's called latent heat. And this is the energy you need. Dudes, come on. This is the energy you need to change the state and not the temperature. So latent heat of a material is the energy required by a unit mass of the material to change its state to a different state. And everybody forgets the next part of the definition. So latent heat is the energy needed to change a unit mass from one state to another without a change in temperature. And everybody forgets to say that in the exam for the definition. Everybody in the exam says latent heat is the energy required to change a unit mass of the material from one state to another, or whatever. And they always forget to say, but without changing the temperature. Got that? Yeah, please, yeah, no touching boys in class, okay, thanks. That's even worse. You get into more trouble for that. Okay, you got that? Ah, sigh. Right. Continuing. What?
This is on recording.
I know it is.
If this channel gets popular, everyone.
Continuing. Yahya, who made the previous statement. Okay, so you have different types of latent heat. You have what's called latent heat of fusion, and this is the energy required to go from this is melting basically. And latent heat of vaporization, this is, which is called what? No. Boiling, thank you. The energy required for boiling. So please note these two words.
Are we going to do fission and fusion?
That's a totally different chapter, but yes we are. Lee, you should write down the word fusion and vaporization.
Is there a way to get the glands law?
Oh yeah.
There's a coach service.
How much do you pay for it?
It's kind of a bit pricey. It's like, I don't know, €10 return trip.
Where is a nice place to go to as a natural place that we can get on the dot or the Dublin bus?
Yeah, and it's like easy to get to, in other words. I always try Spookies. How natural do you want it? You know, like
as natural as Bray, or like there wasn't much in Bray, but like Glendale, that's nice. Like we need a car to get there.
Yeah.
Unless you're willing to give me your car. I kinda have a license back home. I drove for a year without the license because over there I failed the exam 5 times. And that's really
this
normal.
is not
No,
winning
that's
your
really
case.
normal. Like my friends who have their license, they failed it 7 or 8 times until they got it.
This is just to make more money.
Yeah. But I failed it 3 times without them wanting to make one.
So you're just naturally bad. That's what you're saying.
I'm not bad.
What you could try, Faisal, you see, the by almost definition, the more remote country places are not going to be connected by public transport like the bus or the Lewis. So you either got to be willing to take a coach, which is not too expensive, but
The dart, we can get on the dart, it's fine.
Or the train?
Yeah.
Yeah. So if you head further north, if you went far enough north, you might be able to get. You see, some of these natural sites would have free buses that would like go from the train station to the site. Now I don't know which ones, but I'll tell you which website to go to. There's a website called something like Heritage Sites,
Okay.
and they list all of the public heritage sites.
Mhm.
You can look at which ones are along the sort of east coast,
Mhm.
and I would say these are the ones most likely to have a shuttle bus because they'll be nearer to the train station. So you can actually find a site that you like, and they will give you. The other nice thing is the website will give you instructions on how to get there by public transport. So there's always a way to get to it by public transport. It's just how easy or difficult, you know. But Heritage Ireland, and the other thing is, you pay for some sites, and some sites are free. But for all the sites, you can get an annual card for free access, which is only like €30. But it's really good because some of the sites are like €10, so it's like worth the money. Check out that website, Heritage Ireland, I think it's called. Okay, we got these two. Right. So the formula. Well, I'm sure someone maybe knows the formula. The last one was MC delta theta. What would this one be?
MC delta. MC
M delta theta.
There's an M and there's a C.
That is only half right.
Yeah.
ML. The energy required to change m kilograms of material, but not change the temperature. So since you're not changing the temperature, you don't care about the C or delta theta. It's given by the formula ml, where L is the latent heat for the material. The L is like the C.
Is that the same value?
No.
So we have that on the table.
Oh.
See, those lessons where you don't need to use your brain and just use the formula and this times this, you get the answer, I don't like.
That's life. Okay, you got that? What's the units for L?
Joules.
No.
What's the closest answer so far?
The only answer so far. So yes, the closest so far. Anyone else?
It is joules kg negative.
No.
In other words, known as joules per kilogram.
Yeah.
Yes.
Yeah, but that's not the...
No, I tell you why. Because the
Yeah,
Q
just look.
has to be energy, joules. So what do you do to get the joules when you have a mass?
Multiply by mass.
You multiply by negative of mass, so you cancel the masses out.
Yes, or
That's how this master mind works.
yeah, or you could Q is ml, so L is Q over m. That's in joules and that's in kilograms. So that's how this mastermind works.
Watch. Look at the same answer.
Yeah. All right.
Could
Oh,
you explain the state of mass?
yeah, like solid, liquid, or gas.
Of mass mkg.
Yeah. So it's the energy you need to change the state, but not the temperature. In other words, to melt or boil. Right. Now. Yes? What's wrong, Tyrone? You got this?
Yeah.
Now, some things to note. Water will freeze at 0. Water will boil at 100, obviously. Latent heat of fusion of water, okay, 334 kilojoules per kilogram. So you need an amazing amount of energy to change from a solid block of ice. Like if you had 1 kilogram of ice and you wanted to melt it, you would need 334,000 joules at least. Now, why do I say at least? Well, because the ice might be at something like -5. So first you would have to warm the ice from -5 to 0, then melt it. Yeah.
Why is the word fusion used for melting?
No, yeah, fusion meaning like going from solid to liquid or liquid to solid. So the fusion part, I know it sounds quite different to melting, but fuse means, you know, to put things together, so to make it solid. But the thing about latent heat is it works in both directions. So the energy you would need to, you know, to kind of to freeze it, and then, or the energy to melt it, like it's the same number. The only difference if it's a plus or a minus. So when it's melting, you need to give it energy, you know. Okay, continue. So next, the vaporization is even bigger. 2,265 kilojoules. In other words, making steam is much more, it's very energy demanding.
There is an application that I'm signing up for to test the better version of this application. What this application does, it's an alarm. And this alarm wakes you up, and you wake up, and you close this alarm, so you use the application to wake up, you get rewards. Like you collect points. I told everyone about this, and I told them sign up. You collect points. Then those points you can use them for my taxi, and you can use them for other things in Ireland.
If you use this alarm to wake up, you get points.
Yeah, you're the one who set the alarm up.
Yeah. So why not set the alarm like every minute, yeah.
Don't know, but that's how it works.
Maybe there's a limit
I'm
per
pretty
day or
sure-
something.
I'm pretty sure they- I'm pretty sure they put the limit on the time as well,
Yeah,
like
they
you
have.
can't set it at like 1
Every
p.m.
3 hours. Yeah. Yeah, but like,
Did you use
way
it?
to go Ireland.
Did you use it?
I just got the email that
Yeah,
you
me
can
too.
you can download. You signed up?
Yeah.
Oh, now you can get rewards and get free taxis and.
They're lying, that's my
And
sad.
and they want proof of English and an interview.
What now?
You get an email from.
For your IELTS, you need at least 6 points.
Yeah, but maybe, which university is this?
Yeah,
But they might take EAP. You need to talk to your tutor. But the thing you need to worry about is the test via Skype. So this sounds like an interview. Who's your tutor?
You got an email from the IT
Yeah.
saying,
Interview, Skype interview.
why didn't I get this?
I have no idea. I don't know, really, I don't. Okay.
You
Note
apply by
that.
yourself to the IT?
Alright, continuing. Hey! Why so? Continuing.
That's squishy.
Note that water could be liquid at 100 and is in fact liquid at 100 and will stay liquid at 100 until it gets enough energy to become steam. Yeah, I know. Likewise, water could be liquid at 0 until it loses enough energy to become ice. So just because it's 0 doesn't mean it's ice. It could still be liquid. And just because it's 100 doesn't mean it's steam. It could still be water, liquid water.
The slushies are at 0.
Yes, if they put ice in it and mix it together, they'll be at 0. Correct. Go physics and slushies. Right. Imagine a block of ice at minus 20, which is slowly being heated in a microwave. First, the ice will be at minus 20. Then, it will warm up until it reaches 0. Then what happens next? Remains at 0 for some time as it melts. Then it becomes liquid water. Then what happens? It's at 0 at first and then warms up to 100. Then what happens? Stays at 100 for some time until it boils, and now the steam will be at 100. And then what happens? The steam will start to warm up. Now, what will really happen in real life is the steam will release out the back of the microwave through the vent. But if you block the vent, don't do this.
The microwave will explode.
Well, the steam will continue to warm up, which means it'll probably expand, which means it will explode. Yeah. And physics. Yes. All right. So here's one I want you to try now. How much energy do you need to bring 1 kilogram of ice at 0 to steam at 100? So I have a kilogram of ice, and I want to make it into a kilogram of steam. Calculate.
Wow.
So,
Yes.
do this question, please.
The alarm is a challenge. You have to do the challenge, then you wake up. Like it will be a game to win or something. If you don't win it, it will keep on ringing.
That's so nice.
It is nice. It is nice. Now please do this. Yeah, that's true. Because I can say, what, did you not defeat the challenge or something?
The challenge is about to remember 1 kilogram ice to steam.
And that's not using latent heat, is it?
It is. Because ice is a different state to steam.
Okay.
1, Yahya and Faisal, please calculate the answer here. You have an answer, Lee? Please. Give me.
Oh, wait. I don't know.
That is. I'm done.
Don't we need a table for
No.
the values of L?
I just gave them to you 1 minute ago.
Because he didn't copy them.
I did?
Where are they?
Here, I'm here.
That's it? Only 2?
Yes.
Okay, I have those. I wrote them. Okay, never mind.
We don't even need to calculate anything.
No, you do. Do you have an answer, Juan? Okay. What answer do you have?
Yeah.
Because it's big, it should be a huge number. Yeah, it's like megajoules. So if you had like a 1 kilowatt kettle, that would take 20 minutes or something? Something like this? So we can put like 100 kilograms, like a cup of ice into a kettle and switch the kettle on, and 20 minutes later we'll get steam.
Is it this?
Yes, looks like it.
You just add them up.
Three things to add up, isn't there? So this is...
3.
Oh,
So
oh, then you're wrong and you're wrong. There's
Ice.
3 things to add.
ice to water and then water to steam and then multiplied by the...
No. Go back, watch. Look. Move forward. Get out of my personal space. I need a personal zone. Get forward. There we go. Right. How much ice do we have? 1 kilogram, and temperature? 0. Then it becomes...
1 kilogram of water.
That's water, by the way. 1 kilogram of water at what temperature? 0. Then it becomes 1 kilogram of water at 100. Then it becomes steam.
So 2 times.
So first you need an ml, then you need an mc delta theta, then you need an ml again.
Oh.
Yep. Yeah. Now what's nice here, the M is only 1. So because the M is 1, then this will be the latent heat of fusion plus 418100. Huh?
Plus LV.
Yeah, plus L vaporization. What is latent heat of fusion, did I say?
334 kilo.
334 kilojoules plus 418.1 kilojoules plus, and for vaporization?
2265.
Kilojoules. So if I add the three together, 2265 plus 418.1 plus 334, yeah, you get 3.02 megajoules. So just so you know, guys, if you had a kettle and it was 1 kilowatt and you filled it up with ice and you put in 1 kilogram of ice, this would take 50 minutes before you get steam coming out. The reason I'm putting a lot of emphasis on this is I want you to fully appreciate the huge amount of energy it requires to heat water, and even bigger amount of energy to heat water and to make steam. So making steam, especially from ice, requires a huge amount of energy. So in your home, the thing that uses the most energy is the thing that heats the water, whatever that is, gas, electric, whatever. Hot water is very energy demanding. And just before going on to the next example, I just want to demonstrate this. For example, what temperature would you say the water is in your shower?
No.
20?
Your shower is so cold.
What temperature would you like it to be?
40.
40, okay. Now,
40 is not hot enough for me.
okay, fine. Let's just say you want a temperature.
35.
30 is a lot. This one is your body temperature. You want something way hotter than your body
No.
temperature.
But 40 is hot.
Get nice and clean.
I think we did
Yeah.
50 or 60.
Alright, well I don't care, I'm going with 40.
35.
63.
Impossible.
35. 35.
That's colder than your body.
Alright, we'll compromise. 37 and a half.
No.
Right. Now, what temperature is the water going in? That's about 15. So, let's just work out the energy per litre. So what's the mass per litre? No, the mass of a litre of water is 1 kilogram. So how much energy do you need here? MC delta theta, which in this case would be, what's that, 17.5? No, 22.5. Now that's a big number. But what you could do, what you see in some homes, and let's work this out. 22.5 times 4181. That is 94 kilojoules per litre. So that's how much energy you use every time a litre of water passes over you. Sorry, delta Q. Now, what some homes are doing is before the water goes into the shower, it goes down to the earth, really long distance, and then back up, and then goes into the shower. Because down here, the water up here would be at 15, but here it'd be a little bit warmer because of the earth's insulation, and not much warmer. It'd be only maybe like, let's say,
20?
maybe 20, we'll say, at most. And you might think, well, that's not going to be hot enough for a shower. But that's not the point. It's not making it hot enough to be for the shower. It's just trying to make this number here smaller. So you're able to make it 5 units smaller. So how much energy do you save? Well, let's calculate it. So the new answer would be, it'd be 73 kilojoules. So 94 minus 73. So you save 21 kilojoules. And this doesn't cost you any energy to do because the water just flows down and back up. The only energy required is the energy to drill the hole. No, not even to push it. You might need a pump, but it's driven by pressure of the pipes, so you might not even need a pump. What some homes do as well is the water goes up to the roof and then back down, and there'll be some kind of glass here. So what little heat there is, it will warm the water slightly. Again, not enough to make the shower hot, but enough to make it cheaper.
Why can't they pass it through the heat the water?
Yeah, you could do the same thing. The water that could go down then could go through the heaters. So you use less energy to warm the heaters. Yeah. So if you really want to save energy at home, the first thing you should look at is what you can do to make the water easier to heat. Then the next thing would be to heat the home itself. You know.
But they also heat the water by the sun.
Yeah, by the sun as well.
Only the sun.
Only the sun, yeah.
How much do you get sun over here?
Yes.
In Ireland.
Yes, I know. It will not make it warm enough to have a shower, but it doesn't need to, because even if it made the warmer 1 degree higher, then you're saving energy. And it doesn't cost you anything to have the water run through some glass or pipes under glass. Huh? Well, cooling is easy. You could just have it come out of a pipe and back into the house. You know? The cooling is not a problem, it's the heating that's the problem. Okay.
That's a problem here in Ireland.
What? Heating or cooling?
Cooling.
Like heating is like for free.
Yeah.
Okay. 200 gram cup of water has 10 grams of ice added to it. They are mixed together until they reach thermal equilibrium. How much energy would be required to bring the mixture to 10 Celsius? Alright, I want you, we'll do this one together. Is that the drawer? No. Faisal, are you going Super Saiyan over there, or what's happening? You okay?
Do ACs require lots of energy to operate?
They do.
As much as the heaters?
No?
Of course not.
No. They wouldn't be too far away from the heaters. They wouldn't be.
Then you said cooling doesn't require...
Yeah, in Ireland.
You were joking.
Right. Let's have a look at this one. You have 200 grams of water, and then you put in some ice. How much? 10 grams of ice, and you give it a good mix until the temperature is the same, until it's all in equilibrium. And then I want you to give it some heat until the temperature is now 10 Celsius. So obviously the ice is melted, because you can't have the ice at 10 Celsius. So the ice has melted. So I want to know how much energy is needed here to here. Again, it's just a matter of using the formulas like you did a minute ago. Should only take you a minute to do. Please do it now. Thank you. No usher in class. Who then?
Everything. No, or the next door.
No losers in class, please.
This is all from my headphones. They're so loud, they're so nice.
Put them on. Good. Got an answer?
You feel the bass. Feel the compression on your head. So nice.
Ah, that explains a lot. Explains a lot. One, do you have an answer? Should be big, but not as big as the last one. What did you get?
Not that big.
Yeah, okay, what you get? So 12 kilojoules. That's big enough. Yeah. Okay.
Wait.
No, it shouldn't take this long now, come on.
Oh, this is only ice water.
You mix the ice with the water, and then the ice melts in the water.
Oh, it's from up to down.
Yes.
Can't go from down to up.
Yes, as well discussed in the previous lesson. Okay, so let's think about what's happening here. At the beginning, you have how much water? 200 grams. And how much ice? 10 grams. And the temperatures of them? 0 at the beginning. Then later, what's the temperature of the water? 10. And the ice is now also water as well. And they're both at 10. So, let's look at the water, and then we could look at the ice separately. So the water starts off at 10, at 0, and increases at 10. Well, that's just MC delta theta 4181, 0.2, and 10. Right? No, I'm not finished, of course. That's 8362. Now, let's look at what happens to the ice. So first the ice is at 0, then it melts, and then it becomes 10. How much energy to melt? What's the formula? ml.
Yes.
And then when the ice melts, it becomes water, so then it's MC delta theta. So this is 0.1, and what is it for water? The fusion?
334 kilo.
Plus 0.1, 4181, 10. Thank you. Guys, these are 0.01s. Whoa.
So you have to add both the formulas every time you...
No, what's happening here, Yahya, is the ice is melting and becomes water, and then the water warms up.
So it's like 2 steps.
It's 2 steps, exactly, yeah. 0.01 times 334000 plus 0.01 times 4181 times 10. So this is going to be pretty big, 3758. It's pretty big considering it's only 10 grams compared to the 200. Yes. So you get a final answer of 12 kilojoules. Now that has to be the door. Oh, I think I know what's happening. Hey! How many people are out there? And who are you with, Lorraine?
Yeah.
Can you guys use Cab instead? That'd be awesome.
Stay out, come on. Nathan.
Nathan.
Stay out. Be good, huh?
What?
Okay.
Hang on. No, I know you have 5
Stop blaming me for everything.
Andrew! It was a habit, by the way. Sorry.
I'll tell you something.
Right. Now, guys, I know you should be in Cav, but it's more convenient for me to stay in this room because I have
So what is that?
I have 3 hours. So
Can we not just skip the class? Like,
that's Lorraine's decision. Anybody who comes by, I'm just going to redirect them to Cav, including Lorraine as well.
Cap.
Because that's where I should be, really, but we're not moving, so.
Come on. There's a lot of others.
Faisal!
No, did you get the thing?
Rahman.
The quote thing,
Yeah,
you
talk
know
to you after.
Rahman.
Yeah, sorry.
GTFO.
better apologize.
We're done.
I did the thing,
Well,
the survey.
You lost, just give up.
Wait,
You
come
lost.
back. Hope you gave me 6 out of 5.
You'll see, I actually made like a comment at the end, but like, you know, like.
And I'll look through them, I'm like, this one. I know it's anonymous, but this one's Rahman. I'll be able to tell it's yours. Alright, bye. Right. Huh?
You did some.
It did teach them.
Did.
Yeah, it did. Yeah.
Gone with the wind.
I've lost my train of thought. Oh, yeah. Is that question okay? No, Fuan was about to ask me something. Faisal, please. No, question, Fuan. Go ahead.
Don't beg me.
Fuan! What was your question, please?
At the first, the water can't be in liquid.
At the beginning? What do you mean?
It can't be.
The water can't be 10?
Yeah.
What temperature is this water?
No. At what part can't it be 10?
The first one.
It's not at the beginning. At the beginning it's 0.
The water.
Yeah.
The water. The ice is 0.
Yeah, and what you do is you put the ice in the water and mix it.
But the water is not 10 degrees.
Yeah, it'll be 0. The same as the ice. You mix it together.
Why the water is 10 degrees?
Because later I asked,
But the water, why is 0 degrees?
yeah, this word here, thermal equilibrium. You mix them until they're the same temperature. The only way it can be the same temperature is 0, because ice must be 0. But water could be 0. So the only way it could be the same temperature is if they're both 0. Now, I did that, Fuan, I did that sneaky English on purpose because they did that in an exam a few years ago where they didn't give you the temperature, they just said the water and ice are at thermal equilibrium. So most students figured out that that means they're both at 0 degrees, but not everyone. It was a little bit sneaky, but I'm warning you now that you could get it like this in the exam. Okay, Yusuf? Okay? Okay. Okay, can I continue for on? No. Well, I was, we'll go with, we'll switch to maths mode now.
Can we get with
No. Because I'd rather finish sooner than finish later.
We could take tomorrow previous month.
You don't want to switch to maths mode?
Yes, I want.
Yeah, I think we have plenty of physics now. But wait, hold on! I still have 2 more examples to do.
So I think we'll maybe
But we'll continue it in the next physics class. Because I think you've had enough physics for one afternoon. Now we'll switch to maths.
just
Shut up!
I think we're going to be functioning in